All right, so thanks for coming, everybody. This talk is about beman.exemplar. It's not just about beman.exemplar, it's also kind of about the infrastructure for the Beman project that is kind of propagated out to all of the other Beman libraries by first being installed into beman.exemplar. So the first part of the talk, we're going to kind of be talking about exemplar, how it works, and its infrastructure, and then later we're going to be talking about how we propagate that out to the rest of the libraries in the Beman project. So if you're here at C++ now, first, I guess, just an overview of the project, of the talk. First, we're going to talk about the exemplar project structure. Then we're going to go into dependencies and the packaging system that we've developed for the Beman project. We're going to talk about how we've enabled C++ module support in the Beman project. We're going to talk about all of the GitHub Actions-based CI workflows that we've put together. And then we're going to talk about template drift, which is essentially the problem where you create a library from an older version of the exemplar template, you add updates to the exemplar template, and then the library that was based on an older version doesn't get that update. So how do you propagate those out? So if you're at C++ now, you probably already know about the Beman project and what it is and what it does. But for the people that aren't already familiar, the Beman project is essentially created because people who are writing reference implementations for C++ standard library proposals needed better options. It used to be that most people who would create these proposals would put their library in Boost first, but that has various disadvantages, including the fact that if your Boost library is approved, you more or less have an obligation to provide API stability. So if the standards committee requested a change to your library and you had already settled on a stable API in your Boost library, you wouldn't get the implementation experience before it went into the standard. And then you could always roll your own implementation, but doing so requires thinking about a lot of CMake and infrastructure details that aren't really directly relevant to the project of standardizing a library. And a lot of users would essentially just put a compiler explorer link to their implementation in their paper. That's not ideal because it's not really discoverable, and it doesn't give you, although compiler explorer can get you pretty far, it doesn't really give you a great way of having a proper CI continuously tested, updated infrastructure. So what the Beman project provides, we have a collection of libraries that are reference implementations for standards proposals. We provide the supporting infrastructure for them. We have a project template for creating new versions of, new libraries, which is beman.exemplar is the name of that template. We have a Beman standard, which enforces various standards for consistency and quality, for example, that all the libraries have to have examples and tests. And then we have a really great community of developers that help out with things like reviewing libraries and making sure that everything is in order. We have a different maturity model than many libraries. Libraries start out as under development, and once they go through a review process that's similar to the Boost review process, they go into the production-ready category, but that production-ready category still doesn't guarantee API stability because the standards committee hasn't gone through it and made all the changes that they may want to make. Once ISO approves of it, then we can call the API stable, and then we want to keep that library around and actively maintained for 6 years. After that 6-year time span has elapsed, we don't get rid of the library, but we no longer actively maintain it, and we encourage users of that library to switch to the standard library's shipped implementation of whatever the library is. So that's kind of the background of the Beman project. Let's start moving on to the actual project template itself, beman.exemplar, and its project structure.
Eddie?
Yeah?
What happens if it doesn't get accepted?
So there's the line below production ready goes to a line that says early retirement, And so if it doesn't get accepted, then it's essentially immediately archived. And we actually have a library that happened to, where I don't know if it wasn't accepted, or I think the author may have just abandoned the proposal and gotten feedback that it wasn't a good idea, but beman.dump is a library that happened to, and that's currently in an archived state. So the project structure of the exemplar template, this is what it looks like if you run a tree command on a newly generated stamp of the exemplar repository. The exemplar repository doesn't actually have all of these specific files because I've called this new library beman.sample, whereas in exemplar you have a beman. You have a library that implements an identity function, whereas here it's just filled with to-dos because this is intended to sort of be, you're supposed to fill in everything labeled to do in order to get started with your project. We provide, of course, CMake lists files to configure the project appropriately. We provide a CMake presets file. This means that you don't need to manually figure out a build and test workflow. There's a workflow provided by the preset that will set all of that up for you. We have various forms of documentation. The README is sort of intended to towards users who want to just use the library and play around with it and not necessarily make commits, whereas we have a separate contributing file that goes into more detail about how to build and use the CMake for various custom workflows. And of course, we have a license file, which is usually the Apache 2.0 with LLVM exceptions license, which is the same one used by libc++, although we also allow the Boost software license, and some libraries use that license as well. We have these VC package files. Some of these are template files, some of them are configuration files. We'll get into what the contents of these look like later, but they're to support our VC packaging infrastructure. We also have this lockfile.json file, and that is intended for the fetch content-based packaging workflow, which we'll start talking about soon. And then, of course, we have the actual C++ files themselves. So the first thing that I want to talk about, yeah.
Yes, so before going from here, so does this implies that all the libraries must be header only?
So that's kind of something that we want to give users options. Up until a couple of weeks ago, when users would stamp out an exemplar template, it would give you the option whether or not you want a header only or a static library. I had to remove that recently because I added support for modules, and there was kind of a merge conflict there. But it's not an inherent merge conflict. It's something that I have on my to-do list to fix. So I think in the future, we'll bring that back, and we'll give users the option again that they can have libraries with CPP files. But at the current moment in time, yes, basically, we only support header only.
And the reason for that movement was because we originally supported source files and no one ever used them. Like almost all the Beman projects ended up being header only, and people were wondering why we were supporting this extra infrastructure for something that none of the projects were using.
Yeah, to my understanding, we didn't actually have any projects, I think, that needed CPP files, although I could be missing one or two.
Yeah, I was thinking about this as a good, well-tested exemplar for me to be able to apply myself, but I need things other than just header only stuff. So I was trying to steal what you had.
Well, no, it's going to come back.
It's gonna be-
That's what he's saying. It's going to come back because you used that when you ran cookie cutter, it would ask you, right, whether you wanted it to be header only or not, and then basically you get one more directory tree and some different CMake, right? But
Yeah, like so. To explain what cookie cutter is essentially like a Python library. So if you look at exemplar, it's actually got like this subdirectory called cookie cutter. And what that contains are all of these files except as Jinja templates. And so it will prompt you to sort of fill in all of the parameters for those Jinja templates, and it gives you various options. One of them was the option of whether or not you wanted it to be a header only or a static library. We removed that a couple weeks ago. It's on my to-do list to put it back. We should be able to get it back. The first thing that I wanted to talk about this directory structure, you'll notice that we've got these two files, config.hpp and config-generated.hpp. The reason that we have that is the project has these flag forking rules. And we're all familiar with the ODR problem. You have some header foo.hpp. It has some struct whose ABI is dependent on a compiler flag, in this case the C++ standard. And you compile that into one library. You also compile it into another library, but you use different C++ standards for both libraries. You link those together, and then you wind up with undefined behavior because you're mixing ABIs. So the way that we try and mitigate that is instead of directly using the feature test macros, we're going to define those. We're going to define special definitions for those separately. And then where those are going to come from, they're going to come from this config-generated.hpp file that's going to provide settings for the macros that don't depend on the C++ standard. And then this generated file is going to be generated by CMake. It's going to fix the undefined behavior. And CMake may do some kind of test compilation to determine whether or not it's appropriate to set this to 0 or 1. Now, the problem with this approach, and one of the many reasons this has been controversial, is that a lot of users like to just copy-paste the beman library into their project instead of using CMake to bring it in. And in fact, I think just yesterday we had the results of the annual C++ developer survey, and the biggest contingent of answers to how do you manage your first and third party libraries is just that the library source code is part of the build. Now, some of those people may also be vendoring the CMake as well, but we decided that we also wanted to sort of have a fallback to support people who just wanted to copy the directory, the include directory over. And so the way that we do that is in this vendored instance, the consumer is not going to have this generated file, but they are going to have a non-generated config.hpp file. And what this does is essentially looks for the generated config.hpp file and provides fallback defines if it can't find it. And so this way, we enable users to use our libraries just by vendoring the include directory. So that'll come up elsewhere because we have, in modules in particular, whether or not the library is built as a module is one of these parameters in the generated config. But that's later in the talk, and for now, there's a part of the project structure that I haven't talked about yet. We have this infra directory inside of the project, and this is essentially a vendored copy of a beman project infra Git repository. And here we try and separate out and deduplicate all of the CMake that we can. The most important thing about this directory, probably these toolchain files. This is how we provide toolchain files to users, and these toolchain files are consumed by the presets. We also have this great beman install library .cmake file, and what this lets us do is abstract out all of the installation logic. So you don't actually have to have your own bespoke installation library per. You don't have to have your own bespoke installation logic per library, which is what we had before. Instead, you can just do a call to beman install library, and it does all the right things for you, which is pretty useful. We also have telemetry. These files were added recently. They only kick in if you use a bleeding edge CMake version, so you need CMake 4.3. But if you have CMake 4.3 and you build a library that's a beman library, you get this really great, you get this file that you can use for, you put it into like a web GUI, and it lets you sort of browse all of the compiles and see exactly how long they're taking, and it helps you debug your build performance. That's a pretty great thing to have for all of our libraries. We also have this useFetchContent.cmake file. Yeah, go ahead, Jeff.
So the telemetry.shell is probably not portable to Windows.
It is. I mean, you can install, like I tested it on Windows, and it will, if you have git bash installed, which a lot of Windows users do, it will pick that up and it will run it as bash. And there's actually a warning if you run it on Windows, if it doesn't find bash, it will tell you you need bash, and you actually also need JQ in order to get this running. But I've tested this on Windows with those tools installed and had it work.
And I guess, is it, like, do you have to opt in somehow to this?
No, it just comes by default.
Okay, but then if they don't have the right environment, the build will continue anyway?
Yes.
Okay.
It'll just give you like a debug message saying skipping build telemetry.
Okay, cool.
Use fetchContent.cmake. This is part of our fetch content dependency provider system, which we'll go into in more detail soon. And then we have this beman submodule file. That's part of our mechanism to make sure that the contents of this vendor directory match the contents of the upstream beman project infra repository without actually needing to use a git submodule. And later in the talk, we'll go into why we have that mechanism. So moving on, we're going to talk about dependencies and packaging. And the first thing that we did with the beman exemplar project was we just had this very simple fetch content approach. You see this all over the place with CMake libraries, where most of the libraries needed the gtest library to install their tests. And so you can write these CMake statements, fetch content declare and fetch content make available. And what this does is it's going to just pull down Google test from this upstream repository and essentially like make it available as a sub-project inside of your CMake project. And this is really convenient, but it causes problems. And here is a simple example to illustrate what kind of problem that can cause. So let's say we have like this very simple library bar, and all bar is gonna say is it has this function bar that gives you back a string, and it has this very simple CMake list. It's using a file set, which is the post CMake 3.23 mechanism. That's essentially the modern way to configure things that we use. And let's say we have another library foo that depends on bar. The C++ file is equally simple. It just returns what bar returns. But the CMake list starts to get complicated because we're having installation logic here. And so we're bringing in bar via fetch content. We're saying that foo depends on bar. And then we're going to try and install foo. But if you look at our installation logic here, you see that we're installing both foo and bar. And it's not a good practice to install your dependencies for a lot of different reasons. You don't want two libraries installing the same dependency to stomp on each other. But the fact that we're using fetch content here actually, to my understanding, forces us to use this best practice.
But if the bar library has had its own install directive, wouldn't it pick it up? Why do you need to put it?
So that's what I'll explain. It's because it's not being installed. It's because it's being added as essentially a sub project of the overall CMake project with fetch content. So let's sort of look at what this install logic is going to try and say. It's going to say, I notice that foo depends on bar, and that can go one of two ways. Bar can either have come from find package, it's an imported target, in which case CMake understands that the consumer of foo will probably also get bar from find package. So we don't need to install bar. It understands that you're not supposed to install your dependencies. But if bar is not an imported target, then CMake thinks that it's part of the same project as foo, and it actually requires that bar is in the same export set as foo. So if we actually try out taking bar away from this install command, we get this CMake error that says target foo requires target bar that's not in any export set. And so this is like really unfortunate and essentially like the root cause of this. Brett, yeah?
Why not just make another export set for bar and just not install it?
That probably works.
So if you make a component on every install command and just don't install everything, you won't install everything, you just say install foo and you install foo.
But you're putting lipstick on a pig, right?
Right.
So all the problems that we talked about before about like diamond dependencies and libraries stepping one another doesn't solve any of those. It just gets you past this one error message.
What?
Putting it in a separate export set just gets you past this one error message.
No, like you're saying, instead of like just don't have an unqualified install that doesn't have, you don't have the component field, which is exactly for this, is disambiguating between a foo install and a bar install.
We can talk about it after. I'm pretty sure you're going to get an error message anyway.
Okay, that might be true.
Damian?
Eddie, if instead of fetch content we had done add subdirectory, would we have the same problem?
I believe so, yeah. Fetch content works analogously to add subdirectory.
It's not the same problem.
Okay, we can talk about it.
Right, so the root cause of these issues is essentially that package management is out of scope for CMake. Unlike Cargo or UV, CMake only configures the build. It's not a package manager, or at least it's not supposed to be a package manager. CMake wants these raw find package calls that pick up dependencies installed by a separate package manager. And so what we did in the Beman project was we took all of our calls to fetch content and we replaced these with these find package calls. And so although we did this, the fetch content workflow is, although it's sort of incorrect for various reasons, it's very convenient. And so we do support kind of forcing CMake to manage packages anyway, and we have this fetch content dependency provider. And the way that users include that is they just specify this project top level includes equals usefetchcontent.cmake, which comes from the info directory. And CMake provides this set dependency provider mechanism where when a call is made to find package, we can provide some hook that under the hood is actually using just fetch content declare and fetch content make available. These statements are excerpts from the contents of usefetchcontent.cmake. And for a while, this was essentially the only packaging workflow that we supported, but recently we've added support for,
By doing this, it subverts that other problem?
No, it doesn't solve the problem. You still have all of the same problems, but at least what you get is that you have this find package call, so you don't close yourself off to the proper workflow, right? Like if you're using fetch content, you are explicitly opting into fetch content. It's just not being done by default.
If you don't do it this way, then you have to have an if statement in every project for every find package for, is it fetch content or is it find package? And nobody wants to maintain that.
So we decided to add support for VC package to have a proper package management workflow. VC package can be used basically in two modes, which the first one is manifest mode. That's just going to contain a very simple configuration file specifying the project's version and its dependencies. And this is sort of used if you're like a developer who's iterating on the package. You're providing a toolchain file that's provided by VC package. Alternatively, you have classic mode, and we have these two configuration files for VC package, whose contents I'll discuss on the next slide. But what they support is the actual VC package install command. And so these configuration files, they look like this. You can see I'm using UTF-view as an example here, which will come up as in a lot of these slides because UTF-view has a dependency on another Beman repository. and which is beman transform view. And so you can see on the left it's depending on beman transform view, but it's also depending on these VC package packages that are meant to support the CMake file on the right, which is essentially, to my understanding, bridging the gap between our CMake installation and the CMake logic that VC package expects. The reason these are templates, first off, you have to fill in the version, but you also have this SHA-512 parameter where when you have a release, you need to be able to provide VC package with the hash, the SHA-512 hash of the tarball that release ships. These template files get stamped out when you do a release. We have a GitHub action to do that, and they put those template files into this thing called a VC package registry. As well as a release workflow, we also have a CI workflow for this. So when you push a pull request, you have a test that pushes these stamped templates out to a mock VC package registry and ensures that your package still builds. So you can't merge a commit that breaks the VC package port files.
Just to be clear on the port file in particular is kind of like a preset. It's like how do you drive CMake? For that, and VC package wants you to clarify that per package. So it doesn't quite like change the inside of your CMake list. It adds a driver that happens to be also implemented in CMake, if that makes sense.
Yes.
Right.
And so the workflow here, so yeah, we have a release process for doing releases, and I'm assuming what you're saying is this is automatically triggered, but the actual files that stay in the repo always maintain the template part.
Yes.
So that it's, okay. So they're just the input to that CI, basically.
Yeah.
And so are beman project implementations allowed to have third-party dependencies?
Yes, they are.
And if they do, how are they supposed to bring those in if those third parties don't support VC package?
Oh no.
What? I don't know what's going on there. Whoever is iPhone 134, please stop connecting to AirPlay. Maybe if I unplug and plug back in.
I'll answer the VC package question right now. VC package doesn't care where your package comes from. If it is on the internet somewhere, it can pull it down. It can be packaged by VC package. If it's not in our registry, and it's not in anyone else's registry, what you can write is what's called a overlay port, which means I have this dependency. It is located here on the internet. Please pull it down and build it in this way, and that just gets rendered into the beman repo. So you can describe arbitrary dependencies using VC package.
Oh, it looks like we're back.
And what the overlay port looks like is just this port file on the right. You just write a custom one of those for whatever third-party dependency you want, and describe how to download it, how to build it, how to install it.
Eddie,
Yeah.
how can, like, I mean, conceptually, how can a beman library have a third-party dependency if it's meant to go in a standard?
Well, for example, it might have a third-party dependency for its unit test libraries. Or it might have a dependency on another beman library, which presumably they're both going to be in the standard. Like
Right.
with UTF view, it depends on transform view as an implementation detail, but once, I think, is it C++29 transform views ship, Zach? Yeah, then we have transform views that are borrowable, which is what we need.
So then the third-party dependencies will never go in the actual user-facing stuff, right?
We don't have.
Well, it's just a reference implementation, right? The library vendors, they will probably provide their own implementation.
It's just the stuff for, and this happens in standard libraries implementations. So like you implement regular expressions or parallel algorithms, they have to get that behavior from somewhere.
Right.
And so often they use something in their toolchain that already exists as the reference implementation. This is just the analog for open source package level. Grab something that exists and wrap it.
Yeah, makes sense.
So I've been talking about VC package registries. Essentially, you're going to have like the main upstream Microsoft VC package registry, and then you're going to have our Beman project VC package registry that you can configure your VC package to look for and find all of the Beman repositories in. This fallback behavior is useful because it means that we don't have to upstream all of our repos. As a digression, people have been asking about Conan. Conan, I've been informed, has a similar mechanism. That hasn't been implemented yet for the Beman project, but we probably will use a similar mechanism in Conan to the VC package registry fallback mechanism to accomplish the same thing. What does the VC package registry look like? So it's got this ports directory. Inside that, it's got the stamped out portfile.cmake and vcpackage.json files that the deployment GitHub action has committed into the repository. And you'll notice that it actually only has the latest port file and the latest VC package, but the registry actually supports older versions as well. And so I'll explain how that works. We also have this top-level versions directory. This baseline.json file is essentially intended to be a last known good configuration for all the package versions that we know work together well. For the Beman project, we just set those all to latest all the time. And then we also have this b- subdirectory, which I think is just to make the directory size not grow too large. But for transformview.json, which has had more than one release, you see we've got these interesting Git tree parameters. And the way that this works is that we're all familiar with Git having commit hashes for the entire commit, but Git actually just hashes everything. So the way that this works is that when you publish a new release, you scribble down what the hash is of just the port file for that release. And then if you want the port file for an older release, you can just find this Git tree parameter, ask Git, hey, like what port file and vcpackage.json file, hash to this Git object, and then it'll just pull them out of the Git history and support older versions like that, which is kind of a neat mechanism. So our release process, it's a very standard GitHub release process. You create a new tag, you can generate release notes, and then you have this publish release button that kicks off a GitHub action that stamps out the templates and creates a commit in the VC package registry.
This is the release process for the exemplar repo or for any
Beman library? For any Beman library. One thing that we want to implement is we don't have support for this new common package specification yet, but now that we have packaging support, we might have like an easier path forward to implement this, and this is kind of the most cutting-edge modern way of specifying a package. So we've gone through a very nice, done properly dependency management setup for the Beman project. So that might raise the question, why are we still vendoring this infra directory? Why is it just like a copy with all of these files in it? And we probably should properly package most of the files in that directory, but there's sort of a problem with the toolchain files, which is that CMake can't fetch the toolchain files without already having a toolchain file. There's the chicken egg problem where you have this is an excerpt from the CMake presets. The CMake presets are specifying these toolchain files, and to run the CMake, you can't run the CMake preset to get the toolchain files because you need to already have the toolchain files to run the CMake preset. So there was a lot of discussion about like, why don't we just use a Git submodule to handle this? And there's a few problems with that. One is there's the user experience where when the preset can't find the toolchain file because you didn't run a Git submodule update, there's not really any way for us to write CMake to make that error message more clear, because CMake hasn't even got into our code yet, because that's how confused it is about the fact that it doesn't have a toolchain file. And then secondly, the GitHub releases really mess up submodule interaction. Whenever you do a GitHub release, it produces these source code tarballs, And those source code tarballs, if you'll notice here, this infra directory is just empty because this was an experiment where we had it as a Git submodule, and the source tarballs don't populate Git submodules. And so when I was playing around with this, I was like, okay, well, that's fine. I'll just like create my own custom release workflow, and it's going to create its own tarballs. But when you do that, it still creates the auto-generated tarballs that don't have the submodules populated. And there's actually no way to turn off those tarballs that are auto-generated. So
That's intentional as a security feature, though. So like, it's not necessarily bad that they.
well, I mean, I can understand.
That debug was exactly a maintainer like screwing around with this process in a hostile way. So GitHub letting you get access to the undemonstrated commit is a feature for that reason. But we can move on.
Yeah, I mean,
There's no problem that has ever been solved by Git submodules.
Yeah, 100% correct.
so what did we do to solve this? Well, what we actually went with was just reinventing the wheel. We have this beman submodule tool inside the infra directory. We've got this configuration file that has a git remote and a commit hash. And the tool has this beman submodule update command that mimics git submodule update. And it's got a beman submodule status command that ensures that the contents of the infra directory reflect what that remote and hash are saying. And then this runs in CI. So we actually can verify no one pushes a commit that breaks the infra directory.
Is beman submodule here a general purpose tool that could be used outside of just the beman project?
Yes.
Cool.
And it's if you want to use it, which you know, maybe don't, but it's available on PyPI. So yeah. So moving on, let's start talking about a different kind of modules, which are C++ modules. So before I start talking about the actual way we configure and set up C++ modules in the actual C++ part of our project and start showing you real exemplar code, I want to start talking about the state of compiler support for modules right now. So let's talk about some problems with import std. Say we have this very simple module. It has this hello command that uses IOStreams to print hello. It exports a module. And we're going to import that module, ignore the fact that there's a name conflict between the name of the module and the name of the function. But we're going to use it to print hello world. So now let's say inside the module, the hello module, we're not going to use import std. We're just going to include IOStream directly. And we're going to include IOStream, and then we're going to consume it, and then we're going to use import std to get IOStream to print out world. As far as my testing is concerned, this seems to work fine. The problem comes if you do the reverse. If you say import std inside of your module, import that module, and then define a standard library include, the compilers tend to be quite unhappy with that, unless you use MSVC, which in my testing has had essentially 0 module problems. And also, Clang trunk seems to handle this specific example well, whereas Clang 22 still chokes on it. And if you try and figure out like what these compiler errors are actually saying, this is the GCC compiler error. So it's saying that there's a conflicting declaration of std allocator, which the IOStreams header is pulling in. And it's saying that you already defined std allocator as this separate thing where the actual string is exactly the same, but it's saying you defined it inside of a module first, so I have no idea what's going on. I can't handle this. And this is actually the first part of what I measured to be, I think, almost 50,000 lines of compiler errors when you do this. So, and for good measure, here's the Clang version of those error messages, essentially the same thing. So this doesn't work, and so we just have to, and so also you might say, okay, well, just don't use import std, just use normal includes in both cases. That's also broken. You get exactly the same class of error messages where it's these spurious redefinition errors. So what we have to tell people is essentially just, if you're using one of our modules because they use import std, make sure if you're doing an import beman.exemplar, don't structure your code such that you don't have any standard library includes after you do that. And the easiest way to do that is to just use import std everywhere. Damien?
I mean, I've hit the same problem last week, but it means that honestly, until they fix the tool chain, this is just not tenable, because it means we would move everything, all your dependency, everything at once would need to be ready. Yeah, it's a mess.
Jeff?
Sorry, if you go in reverse order in the client code and you put the include IOStream above the import, does it work then?
Maybe. I haven't tested that. But by the letter of the standard, I think this is supposed to work.
No, this is supposed to work. Yeah, this is a bug in the compilers. There's no questions about it. You're supposed to be able to do whatever arbitrary order you want to. And yes, that is a migration feature that is killing us from actually being able to do this. But I think if you put the include above and the import below, it will actually work. But
Yeah.
I haven't tried it in the last, 6 months.
Yeah. No, that's definitely possible.
And I think it's a moving target, right? Like, so in GCC, right, there were, I think, maybe you told me or somebody else told me that they had some different problem before that's now fixed, and I think it was you that told me that, and now this one's still on.
Right, yeah, like this specifically with GCC 15, I ran this same example except with including the print header instead of the IOStream header.
Yeah.
GCC 16 can now handle the print header, but it still can't handle the IOStream header. So they're making slow progress, but it's probably, these tool chains are definitely not fixed yet.
Well, and it also mentioned that I'm aware of the fact that, the vendors of the standard library, they have to do specific things for each element of the library for it to work properly in import STD. So one thing that could happen, for example, is if they add a new feature and they forget to put it in import STD, then you might be expecting, oh, well, I should be able to access this thing in import STD, but it won't work because they forgot to do it, and it's a bug, right? And I think, yeah, we're still in that situation where there's a lot of this kind of stuff, unfortunately.
So what we've settled on is essentially just telling people that they can't have standard library includes after module imports of beman libraries. And so with that rule out of the way, we can get to what we really want to do, which is spending all of our time fixing unprefixed standard integer types.
Oh, yeah.
And of course, import STD is still experimental in CMake, so we have to have this set of UUIDs that we define per CMake version in order to get it to actually do the thing that we're telling it to do. So moving on, let's talk about Beeman's approach for the actual,
Just to clarify, that is not even the beginning of that file.
Oh yeah. It's every CMake version. It's every CMake release since 3.30.
They're all the same. They're all the same ID though. Like we don't change it every single day.
Oh yeah, I guess that's true. I didn't even notice that. but I think it does change. Like if you look at for example,
it does change occasionally. When we actually change the API surface, we change the UUID to tell you we've broken this, and if you are expecting it to work the same way, it doesn't work the same way anymore.
Sorry, is there a regex way to do that so we wouldn't have to have so many if-else's?
I wrote a script that spits this file out. But
CMake knows how to compare verbs, sembers. You could write those conditionals, but this is fine.
Yeah, that's fine.
Okay.
Jody?
So is module support something that the Beman users have been clamoring for? Or is this something that you're doing just so that you can try to force the compilers to actually support modules? Because I don't know anybody that actually uses modules.
So it's not something that I've heard a lot from Beman users that they want, but it's actually something that I've heard a lot from Beman maintainers that they want. The library developers, being people who are proposing standard library features, tend to want to be on the cutting edge of C++, and so want their libraries to support modules. It's kind of neat to do so, and we have a way of doing it, so why not, essentially?
And I would just add into that, obviously until projects like Beman can get over the problems that we're talking about here, the users won't clamor for it because they can't use it, essentially, right? So, and, we're on this precipice, I feel like, where we're very close to this actually getting to a manageable state for many projects. I plan to try it in production this year. So, you know, because significant other libraries like FMT, you know, have support for modules as well. And so if you can go all modules all the way, then I think, you know, you're in good shape. And I know Boost is still doing lots of experimentation to try and get there as well.
So how do we get our actual C++ to support modules? We're going to adopt this approach that this Boost developer, Ruben Perez, was putting together for Boost. And the way it works is essentially this. So the basic non-module implementation of a very simple library that just prints hello. You have a hello HPP file. You have a consumer.cpp file. The module equivalent of that, you export a module called hello. You have this function that you export, say hello. You're using import std to get IO streams. And then your consumer is going to import that module and invoke that function. So what we want is essentially to split the difference and have both of these. And the way that we do that is we're going to take our HPP file, and we're going to create this cppm file, this module implementation file. And all that's going to do, it's going to export the module. It's going to import std for the standard library dependencies. And then it's actually just going to include hello.hpp within this export statement. And then that just essentially copies the entire implementation of hello into what that module exports. There's one change that we need to make here, which is that because we're using import std, we sort of need to if-def out this IO stream include because of the aforementioned compiler problems. And so now we can have our consumer import this module, and we're going to say that right now this hello.hpp file, because it's being used to implement this module, we're going to call this included from interface unit mode. And then if we look at the consumer.hpp, we notice that it's saying import hello, but it would be kind of nice if the consumer could just do the same thing whether or not it's bringing in the library as a module or a header. And so it would also be nice if we had like a compatibility mode for the hello HPP header, where if you include it, it just turns into an import statement and brings in the module that way. And so how do we support all of these three different modes for the same header? So this is what the transform view HPP header looks like right now. There's two relevant macros, which are transform view use modules and transform view included from interface unit. If the user hasn't enabled modules, then they just get this normal mode where they have the standard library includes and then they have the contents of the implementation. If we're setting up the module, then we have we're not only defining beam and transform view modules, we're also defining transform view included from interface unit. Then you get the implementation, but not the standard library includes. And then finally, if you're consuming the module, you'll have transform view use module set, but you won't have included from interface unit set. So that's that will just turn the include of transform view HPP for that consumer into the appropriate import statement. And so this is it all put together. And so this approach is fairly convenient. One cool thing about this is that when we combine this with the VC package approach that we had before, VC package has this features feature that lets you specify to VC package which alternative configurations of your library you want enabled. And so beam and UTF view is module enabled now with this mechanism. It has a module feature, but it also is able to tell VC package that, hey, if you're configuring me as a module, you also need to configure beam and transform view as a module as well. And that way we have packaging and transitive dependencies working for modules with our VC package setup. And this is also all tested in CI to ensure that this all works.
Question. The previous header that implements the three, is that maintained per repo, or is there like, is that in the infra part of the code and generated somehow?
So it's an intrusive change. So like if you look at the part that's blue and white highlighted, it's just the implementation of transform view itself. there doesn't seem to be any good way of like separating out this boilerplate into some mechanism that we don't actually need to modify the header files of the actual libraries themselves. So that's what we do currently.
With including a header inside of an export block, I am a little bit concerned about exposing details that are not meant to be exposed. Are you already getting there?
No, I'm glad you asked that because I was going to forget to mention it. But essentially, the thing that you can do here is that you can manage visibility on the per file level, which a lot of library users want to manage their module visibility by having like a macro that defines export and then exporting or not exporting individual identifiers. But if you have like a file that's like detail transform view impl.hpp that's not a user-facing API, you can still include that after the included from interface unit definition, but outside of the export block. And then that way you can get the visibility organized that way.
Cool.
Okay, so moving on from modules, we're now going to get into the GitHub Actions CI. So this is probably the biggest part of the talk. We've done a lot of work to make sure that the CI process for Beman libraries is checking all of the things that we want to check. Before I get into the build and test workflow, a couple of other things that the CI does are it gives you code coverage. So we use this service called coveralls. Coveralls, the most useful thing in my opinion that it gives you is it gives you a source browser where all of the lines of code that you've covered in a test are highlighted in green. This is an excerpt from my UTF-View implementation, and as I set up code coverage, I went through and I just looked in all of the places that weren't highlighted in green here, and I found like, I don't know, 5 different bugs. And so like I think that like being able to see like, oh, where could a bug be lurking? Where have I not tested is like a really useful thing for CI to tell you. It also provides this coverage percentage. And when you have a PR, it'll tell you whether the coverage percentage went up or down. So if you have a new feature and you forgot to add unit tests for that feature, theoretically, the coverage percentage will go down and coveralls should tell you. It doesn't actually block you from merging based on that, but it gives you a little comment on GitHub saying like, hey, your coverage went down, maybe you're interested in knowing that. In practice, the actual percentage is not as useful as actually looking at the files and the highlighted green lines because, for example, if you have a template and you never instantiate it, it doesn't show up as uncovered. It just shows up as not even part of the denominator. Zach?
So also, coveralls will not tell you when you have actually exercised context per code, even if you have, because it can't see it because it's doing a sampling-based method. Right.
So like for UTF-View, the way that I get coverage is I don't use a unit test framework. I just have like a bunch of context per functions that I both static assert and run at runtime. And so the static assert tests that it all works at compile time, and then running them also at runtime gets me code coverage. If you're interested in how that kind of compile time, runtime unit testing difference might be smoothed over, I recommend watching Braden's talk. So next, we also have this pre-commit mechanism. This handles formatting and linting. The nice thing about this tool is that it can be installed as a Git hook. So if you leave trailing white space in your files, then when you hit git commit, it'll just modify the files and do the commit for you. So you don't even have to wait for it to get pushed and for CI to tell you, hey, you forgot to do trailing white space. You don't need to use it as a Git hook. I usually just run it manually before I run my commits. And also the configuration file for this is up to the maintainer whether or not they want each individual check. So for example, I happen not to like Clang format, so I don't run that on my library, but other maintainers do, and it's up to them whether or not they want to have Clang format or not. And at the bottom of this pre-commit check, you'll see that we have this beman tidy check. So what beman tidy is that the Beman standard, all of the rules that can be machine checked are checked by this tool. So for example, it will fail your CI if you try and push a Beeman repository that doesn't actually have any examples, because all Beeman repositories are required to have examples as kind of like a minimum requirement for your libraries. Now let's move on to the actual build and test workflow that's building and checking the C++ itself. So we previously in Beman Exemplar had a more traditional GitHub CI matrix. Essentially, the way that this works is that you've got these 3 different lists in this matrix. The first list is the platform, and so we've got 4 platforms in that list: GCC, Clang, MSVC, and Apple Clang, which is still the set of platforms that we use now. We have a CPP version list because it's a matrix that multiplies, so we now have a unit test per C++ version per compiler. And then we have these different CMake args, and we have like 3 different build configurations that we're building, so we have one of those per C++ version per platform. And the configurations here, we essentially have non-sanitizer configuration, we have a thread sanitizer configuration, and then we have what we call a max san configuration. What that's motivated by is essentially that thread sanitizer is not mutually compatible with address sanitizer, but address sanitizer is compatible with undefined behavior sanitizer, leak sanitizer, all the rest of the sanitizers. So we do essentially, 2 types of sanitizer build, which are thread sanitizer and everything else. And so we can augment this matrix. We can have these include and exclude parameters. We can include a warn error build for GCC and a shared library build, and then we can exclude thread sanitizer on MSVC because it doesn't support it. But if we look at some of these jobs that this matrix is producing, we'll notice some things. First of all, there's too many sanitizer builds. It's probably wasteful of CI resources to run a sanitizer build for every single C++ version. If you have a sanitizer problem in C++ 23, it's probably also going to show up in C++ 17. You can't specify release versus debug. At this point, this CI matrix would just run the release build followed by the debug build serially, which of course takes longer. There's only 1 compiler version used for testing. We actually had a separate matrix that tested different compiler versions, but that actually pinned the C++ standard version to C++ 20. And there's only 1 standard library used for Clang. And so we want more parameterization here, but we don't really know what's the best way to fix that lack of parameterization without having a combinatorial explosion, because for example, just release versus debug is going to double the number of jobs. So let's look at the parameterization in the new refactored CI version, CI setup for Exemplar. We have the compiler, we've got its version, we have the C++ standard, the standard library, debug versus release, and then the build type. So all of these are configurable in the new system, but if we actually look at all of the different jobs, there's 82 total jobs that are configured this way that Exemplar is running for C++ build and test. We notice that unlike previously where we had all these different sanitizer builds, we actually only have a thread sanitizer and a max sanitizer build per compiler per standard library version. MSVC, of course, only having the 1 max san build because it doesn't support thread sanitizer. And then warn error jobs, we have a warn error per, again, per compiler per standard library version. So what configuration language do we use in this refactored setup? Well, it's just this kind of like invented JSON configuration language. And the idea is that instead of this matrix where everything is multiplied by everything else, it's a tree. So if you look at that, the innermost list of tests, because this is Clang, we're multiplying those 5 tests by 2 for libstd C++ and libc++. But that's only for the Clang 22 C++ 26 entry. And then for the C++ 23, 20, and 17 entries, we're also multiplying by 2 in terms of libstd C++ and libc++, but we leave the warn error and the sanitizer builds out of that inner list of tests. So this is kind of like a much more easy and intuitive way of configuring which CI jobs you want to run. So what you see on the slide here is the newest release of Clang. For the earlier releases of Clang, we have something very similar. For Clang 18 and 17, we're modifying the configuration to take out the newer C++ standard versions, but specifically, we take them out for libstd C++ because older Clang compilers and newer libstd C++ versions with newer C++ standards seem not to play nicely with each other, so we can just configure that out. For GCC, we again have these sanitizer builds for the most recent version and standard, and then we have a much more minimal configuration for the older versions. And we do this for Apple Clang and MSVC as well. And so the CI speed, this is a pretty low overhead setup. With Exemplar, we have, at the time I measured this, we had 90 tests. They all ran in about under a minute. And with about 20 CI jobs running at once, if the CI system is uncontended, you get this full CI matrix running in 5 minutes. But Exemplar is like a very minimal library, so that's kind of like a lower bound. Beman execution is a much more heavyweight library. Each one of its tests takes about 5 minutes to run, but its set of configurations is a lot more limited than Exemplar. It only runs 33 of these tests, and they fully run in a little more than 8 minutes, which is still a pretty good CI turnaround. How do we implement this JSON configuration language? We just have this very simple Python set of inter-nested for loops, and that just lives inside of GitHub Actions, and it is just producing a separate row for each entry, and then all of those rows go into this matrix parameter of GitHub Actions that it's able to pick up from a JSON input. One thing I'll draw your attention to is this image prefix, because that's my segue to the fact that we have our own Docker image set up for this CI workflow. So what did we need for our Damien?
I thought you were looking at presets. Why did you guys decide to then reassemble all your options directly?
So we do have CI testing for presets. I don't have a slide for it, but all of the presets are tested. But we also want to support configurations. Like, we don't want to limit users in what we support to what the presets support. Presets are kind of like an easy onboarding option for new users because they don't require you to like figure out a lot of CMake that's custom CMake. But yeah.
So I thought one advantage you would have had if you were using preset to drive your tests is for developers to be able to reproduce in front of them what they did. But here they kind of have to go look in the logs and find out which combination of option work best.
Well, I'll get to that later. We actually do have some tooling that smooths that over a little bit. But first off, building our own Docker images, what we wanted was we wanted compilers and tools pre-installed. I list this because we had one of our CI matrices previously that tested different compiler versions would do so by having the compiler version in the matrix and then using that compiler version as a template for an apt command that would just install whatever compiler was specified during the CI job, which is unnecessary overhead. So we wanted all that stuff pre-installed. We want a fast turnaround time after new compilers are released, because we're targeting the newest standards. We also want the ability to use older compiler versions than the most recent one. We don't want like a pure live-at-head setup. We also want to support. We don't want to have like super old compiler versions. We don't have that much of a need for it, but we do need to be able to say like it's not just trunk that we're supporting, but we also want to support trunk. We want trunk builds with frequent updates, and also we want at the time, and perhaps still, we wanted to be able to support compiler forks, like the Bloomberg Clang fork that supported reflection. We don't need a fork for reflection anymore because GCC 16 ships it as of like a few days ago. But at the time, in order to support reflection for CI builds, we needed to be able to support forks. So what were our options? Ubuntu was what we used originally, but we don't have fast turnaround for official compiler releases or official ways to get trunk builds. I've since been told that there are good options for this in terms of third-party ways to get these packages. But even still, despite that, I think that the system for getting a fork of Clang that you want into a .deb file in Ubuntu, it at least seemed daunting to me at the time. So I tried NixOS, and I got weird errors and got stuck and gave up on NixOS. And then the exact same thing happened with Arch, except with Gentoo, I was somehow able to persevere, and so that's why we're using Gentoo for our Docker images. So if we look at Gentoo's set of packages that they provide for LLVM, the green ones are in a binary package cache. People think of Gentoo as pure build from source every time, but they do support binary packaging. If you look at how far back compilers they support, they go back to Clang 16, so about 3 years ago. That's ancient history in standardization terms. So that's perfectly adequate for us, and actually I think we only build images back to Clang 17. For the newer versions, Clang 22, that was made available by Gentoo the same day as the official release. We rolled that out to beman CI about 2 weeks later. We've since improved on that turnaround, as you'll see later in the presentation. But then these trunk builds, I don't know if you can see, but in addition to the actual LLVM head trunk build, they have these date-stamped builds that are essentially tested by the Gentoo maintainers that they work, whereas frequently the actual head LLVM build will have build problems that Gentoo hasn't worked around or fixed yet. And these date-stamped versions come out pretty frequently, so this is a pretty good solution for trunk builds. For compiler forks, there's a way of doing it. We had a fork of the Gentoo package registry where I just manually changed the source for the LLVM package to the Bloomberg fork and the branch appropriately. And this worked for a while, and we got our compiler fork Clang image. Eventually, the scheduled CI builds just stopped working for this, so it's since been dropped. But at least we have the proof of concept that this system can support compiler forks. We have GitHub Actions that build these Docker images. For the compiler versions that happen to be in the Gentoo package cache, we build the images in about 20 minutes. When we have to build from source, it's a lot costlier in terms of time. We're actually running into this problem where GitHub Actions limits you to 6-hour compiler to 6-hour total builds, and it takes 4 hours for Clang to build. I think that I've heard from other people that they've gotten a GitHub Actions Clang build going in about 1.5 hours. So I think what's happening here is that we're doing builds of ancillary Clang tools like ClangD and basically everything in the LLVM package. So there's probably easy ways to cut down on the time here. Damien?
Why do you bother rebuilding older tool chains?
What do you mean?
Well, I assume that's on merge. You're going to rebuild all your containers, right? Presumably, you only care about something that changed.
It is smart enough that if you only modify the configuration of a binary cache compiler, it will not go and rebuild the from source compiler. So that saves you a little bit of time. And these also run on a schedule, which is kind of how you get the latest trunk builds in addition to push.
So, from my understanding, these are images of just the compiler. So you make a layer and then layer it up on top.
It's the compiler plus all of the tools that we need for CI. So actually, one of the things that's nice about Gentoo is we don't just get these trunk compiler builds, we also can get bleeding edge CMake. So we're always using the most recent CMake version. And so that creates, these CI jobs create these set of images with the set of tags, as you can see in this is a screenshot of the README. It's slightly outdated because we now have GCC 16. So for how these GitHub Actions work, I'm going to talk about a case study with my own library, UTF-View. And to understand what's going on here as background, the C++ ranges library requires deduction guides for all of its views. So this is an example from CPP reference of drop view. And these are two equivalent ways of doing the same thing, spelling out drop view or using std_views drop. But the way that the first one actually works is it needs this deduction guide in order to turn the view that comes in into the views all T version of that, which is essentially like a mechanism for the views library to distinguish between owning and reference-based ranges. So I had to refactor how these deduction guides worked in my library, because originally I had all of these, my library is for transcoding UTF. I originally had all of these different CPOs, and each of those mapped one-to-one with a different view, and those had very easy deduction guides to write. They were all implemented in terms of this implementation detail class. SG9 decided that they didn't like that, and instead they wanted the exposition only class to be a bona fide class. So that raised the question, how do we write a deduction guide for this where we're not only deducing all T for the input range, we're also having the user pass in to the constructor this non-type template parameter to UTF-view error kind, which is an enum, and this two-type type template parameter. And so what I reached for the non-type template parameter was this thing that we used to have in the language called non-type T. Non-type T, of course, comes from function ref, because we decided that we had to make function ref more functional, and we figured out that if we added this non-type mechanism, we could save an indirection in function ref. And I know what you're thinking. Why didn't we just use constant wrapper for this? Well, we decided that constant wrapper wasn't a usable replacement for non-type. So great. I can just, non-type is in the standard. I can use it. And I used it. And then one day, I got a notification that non-type was not a member of STD. And you're probably ahead of me by now. You're probably thinking, oh, I know why that is. It's because we implemented constant concept and variable template parameters. So we no longer had non-type template parameters. We had to rename them all to constant template parameters. And so we had a paper to rename std non-type to std constant arg to reflect that. But actually, that's not why std non-type stopped working in my library. It's because we changed our minds that constant wrapper wasn't a usable replacement for non-type. And we instead decided that constant wrapper was the only tool needed for passing constant expressions via function arguments. And so GCC implemented that. My scheduled CI job picked it up the next day for the CI Docker image. I used GCC trunk in my CI matrix for UTF-view. I got a scheduled build, and the next day I got told that non-type had been taken out of GCC. I got an email about this that linked me to the compiler error, and I managed to fix that in both the reference implementation and the library, so that now uses constant wrapper, and I got it done before the release of GCC 16, 5 days later.
Nice.
If only the committee could decide that.
And that's kind of a great story, but the story is over now. Constant wrapper is now in a shipping compiler and a shipping standard, so there's definitely no way that the committee is going to change its mind again and change the design of constant wrapper in a way that breaks my library one more time.
Hey, Eddie, if you wouldn't mind holding your hand over the second name on that.
Story to tell if it's relevant, but I was going to say the deduction guides work through type alias templates that fix specific parameters. I discovered that in recent versions of Clang that now is supported.
Yes, that was something that in even earlier version of the UTF paper did. I still have an outstanding Clang bug for that. There's some part of it that wasn't compatible with the way I was using it, and I think also just wasn't the design that SG9 wanted. But yeah, that's definitely part of the design space. So we had a question earlier about running CI locally. This is kind of the first part of the talk where I'm going to talk about vibe coding. But essentially, the industry standard way of doing this is this tool called Act. And you can just run it, and it is supposed to use Docker and run all of your GitHub actions. I didn't like the user experience with this, and I couldn't figure out how to get it to run thread sanitizer, even though I was passing parameters that were supposed to enable those permissions. So the nice thing about this brave new world is that if there's some general purpose tool that's not working for you, you can just prompt AI to make the special purpose version of it. And so this is an excerpt from the prompt that I fed. You're not supposed to be able to read this, but it's basically just this 2-page prompt that I fed in for how this tool was supposed to work. And it spit out this on the first try. I had to make some changes to it to get it to work. But now you can just run beman local CI and filter exactly what part of the configuration that you want to run. Here's an example of it running all the GCC C++26 jobs, and then that way you don't have to wait around to push to GitHub and wait for GitHub Actions to run in order to check whether or not your commit passes CI. Now, of course, this only works for GCC and Clang because MSVC doesn't work in Docker.
Would you go to, like, you would specifically run this in the container image that beman infrastructure provides, and then you run this? Do I understand that right?
So the idea is that beman local CI is running Docker internally. So it's spawning, it is spawning a bunch of the appropriate Docker containers.
Sure.
We also have another vibe-coded tool. We had this problem where all of the READMEs have this compiler matrix, and we have this CI configuration. We want to make sure that they match. We have this tool, beman README platforms, that does that. And all of these tools are available upstream on PyPI. So the last part of the talk I'm going to talk about is actually how do we propagate all of this stuff from the exemplar template to all of the other repositories. And for that, I need to talk about template drift. And I don't mean this kind of template drift. I'm talking about when you have libraries that drift away when you update beman exemplar. So beman exemplar has got this separated out infrastructure directory. And it's got some C++ that users are meant to fill in, and it's also maybe got some C++ and CMake scaffolding that we weren't able to separate out cleanly into the infra directory. So let's say a maintainer decided to use exemplar. They stamped out a library called foobar. They filled that C++ in with their implementation, and maybe they also made some changes to the C++ scaffolding and even to the CMake. Then we're going to update exemplar, and we're going to maybe make some changes to the infrastructure, and then maybe we also make some changes to the C++ scaffolding, and then we try and port those back into foobar. With infra, it's really easy because we have the beman submodule mechanism, but not everything can be separated out into infra. So we might want to have the C++ changes ported over too, and we have some merge conflict that is difficult to address manually. This is a problem. What has changed in exemplar that we need to go in and backfill? The infra directory didn't used to have this whole mechanism. We just used to have like a CMake directory where we had copy-pasted toolchain files. We used to have raw calls to fetch content. Those needed to be propagated when we made the change to exemplar to use find package instead. The beman install library duplicating the installation logic. We needed to propagate that too. The refactored CI that we've gone through. Even after we refactored the CI, we had to go in and make sure that they were using our GitHub Actions workflows. And then also the change that we mentioned before where we used to have static libraries and we moved to a header-only interface-based library model. So the first thing that I wanted to do was essentially get a status report on how these, which of these libraries in beman had these problems. And I also just used AI to do this. I had a prompt that was saying like, look at all of these repos. I'll tell you what it means if they have these specific deficiencies. And you can essentially just qualitatively read through the code yourself and figure out whether or not they do or do not have these problems. I had a hook that this is hooked up to Google Spreadsheets and had the AI fill it in for me. What I did with this is essentially like organize all of the libraries into which are going to be easiest to address and which ones are going to be harder based on, for the ones that are all green, they had all of the major refactors applied to them, but they may have had some smaller, more recent changes, like for example, the telemetry, the build telemetry that I wanted to apply.
How comes UTF view is not the shiniest?
Well, I mean, one thing is, wait, how come UTF-view is not what?
It's not all green.
Oh, because, well, for one thing, because it doesn't use gtest. Like I explained before, I wanted to get coverage working, and so like gtest doesn't really have good facilities for constexpr. So there's a, I think it's the only red entry in the supported unit test library column. And so I think that previously had made it difficult to switch over to the to new exemplar features. So these are the libraries that I started trying to address first. And the way that I went about doing this was we're just going to stamp out the new copy of the beman exemplar template, and then we're just going to copy over the implementation, but not any of the C++ or CMake scaffolding from the beman foobar library. The way I went about doing this, again, also this is something that is in the wheelhouse of AI. I had a prompt that was just saying, look at the repository and follow this exact series of steps, which is the same thing that I would tell a contributor if I was telling them how to do this. Look at the configuration file for cookie cutter and figure out what all of these parameters are, read through the code. Run the script to stamp out the newer copy of exemplar, copy the C++ code over from the old version of the repository. When you do that, the AI is smart enough to figure out that it shouldn't leave around like a to-do.hpp file, and it should keep around all of the scaffolding, but update it to the intent of what the library is trying to do. We copy over the CI matrix, assuming this library is a library that's new enough to have the refactored version. We make sure that all of the boilerplate and exemplars README is propagated over. And then we're going to just clobber the contents of the old repository with the updated stamp of exemplar that we've produced, and we're going to push a pull request. And this approach scaled actually well enough to do almost all the libraries. For the libraries that I didn't update yet, these were essentially libraries where we had the problem where the maintainers were too good at their jobs and too diligent, and so they did things like implement modules before. When I was doing this project, I hadn't yet implemented modules, so I didn't want to like clobber their module implementation with a version of exemplar that didn't implement it. But this approach is kind of a one-off. It's pretty heavyweight to restamp the entire template every time something in it changes. So now we have this mechanism where all of the libraries, when they get updated to the latest exemplar, they have this file called .exemplar version. And that just contains the git hash of the version of exemplar that they were most recently coordinated with. And so that way we can see what git history the library is missing that's in exemplar but not in the library. And instead of just like applying raw patches, we just have a prompt and we feed each individual one of these commits into a separate AI agent. And then they create a squashed commit that contains all of the updates to exemplar. So this is a video sped up of like my script launching in all of these AI agents. One of the things it's doing here is setting up build telemetry. But we actually also used this mechanism successfully to roll out support for packaging. So we had a commit for exemplar that added this VC package packaging support. And what's nice about having AI apply the change and being able to have it know qualitatively what you want to do instead of just like the actual bytes of the patch is that for beman exemplar, its list of dependencies looks like this. It's just gtest. When AI was applying this change to beman monadics, it was smart enough to know that beman monadics uses catch2 for its unit test library instead of gtest and make that adjustment. Similarly with beman anyview and its benchmark unit test dependency, and beman.utfview with its transform view dependency. So, this is like you burn a lot of tokens with this approach, but I think this is actually like a good way to save time for having the agent do work that you would have to do manually. Rolling out compiler updates. Similarly, you can prompt AI to use beman local CI and it knows how to run it. We had a commit to exemplar after checking all of the library, that all of the relevant libraries supported GCC 16 using this beman local CI check. Luckily, they all just worked without any changes. I added GCC 16 to the CI matrix of exemplar, and then I could roll out that change to CI matrix qualitatively. I was asked previously why updating the CI matrix is an intrusive change instead of just putting it in infra, and the answer is because the CI matrices are different per library. They might support different sets of compilers and standard versions. It updates the README appropriately, and then we have CI updates as part of the squash change, and we have happy maintainers that are happy about the fact that we rolled out GCC 16 to all of these libraries the day after it was actually officially released. So that completes my slides. I want to thank all of these people. Beman is a complete team effort, but all of the people mentioned here were really important to what you saw previously. Brett did a lot of really foundational work on setting up beman and its CMake configurations. River was essentially the primary maintainer of exemplar for a really long time. Vito contributed the VC package registry, among other things. Klaus did a refactor of the beman install logic so that it would support module installation. Jeff has been leading the project and has, in addition to doing some work on exemplar himself, has provided a lot of really helpful guidance. David has been active with the project and has helped me figure out that the module approach that we used was the appropriate one. Mikhail Svetkin, he has a talk here at C++ Now, and his monadics library was an early adopter of modules. So with the few minutes I have left, I'll open it up to Q&A. Thanks.
So some of those VC package files could go next to the version strings, right? Or did you look into that, or have you considered that?
What do you mean?
In the registry, like you don't necessarily need all those VC package files in every repo. You could like VC package itself doesn't require you to add specific VC package files in your tar files to be in VC package. So have you considered that kind of approach?
Well, we only have the templates in the repo.
Oh, okay. So the other ones are in
the registry.
Okay.
Braden?
This is incredible. I think the work you're doing here is really cool. This, to me, feels like more than just an exemplar for a beman library, and almost like a really good starting point for like any C++ project that might not even be related, maybe with a few tweaks to sort of decouple it from beman. Have you thought about that kind of thing at all?
I have, and I think that like it's essentially like, I think that's definitely a worthy goal, but we have to sort of limit the scope to some extent because of the amount of volunteer bandwidth. So one of the things that I looked at was it used to be that if you stamped out a beman exemplar project and it wasn't part of the beman project library, the beman project GitHub organization, that CI would fail because CI needed our organization GitHub secrets to be able to actually succeed. So it was actually pretty easy, and it was confusing even beman maintainers that this was happening. It was pretty easy to go in and say, like, okay, if you don't have the secrets, then we're outside of the, or I guess not if you don't have the secrets, but if you're outside the organization, you won't have the secrets, so just don't run this test. And that was kind of an easy way to make exemplar available outside of the beman project. But in terms of like can I like go through and like do these kinds of updates and adding module support to a repository that someone cloned out from Exemplar that isn't in the Beeman project organization? You know, that's limited by like the amount of volunteer time that we have available in prioritization. Vito?
I was at most of these debates, so this is more just what's your opinion, but there's a ton of work and hoop jumping that's happening here to support every possible consumption mechanism of a given Beeman library, right? So you have the people who are doing it correctly, like they're using a package solution, or they're at least pulling down the CMake and building it locally. And then you also have where, you know, a non-trivial amount of the kind of code that makes average C++ programmers go, this is what's wrong with C++, just to support people who want to vendor the code. Like, in your opinion, where, for a project that is less comprehensive than Beeman, that is, you know, maybe just one person trying to put something out in the world, is there some line you draw? Do you think that there are places where Beeman is being excessive in the amount of use cases we support, or?
Well, I kind of think it's a question of like, who is jumping through those hoops, right? Like if I was starting a project from scratch and I wasn't using the Beeman template, I would not go to any trouble to support vendored libraries. But by the same token, maybe I wouldn't go to the trouble to support VC package, and I would only support fetch content. So I think that like the fact that we have all of this hoop jumping is mitigated by the fact that at least for the most part, we don't test the vendored workflow in CI, but for the most part, we test both fetch content and VC package in CI, for example. So the infrastructure has kind of been put there for you, and if you break it, the CI job will fail. And maybe if you're not in the Beeman project organization and you don't like supporting that, you can just delete those unit tests. One more question, Gasper?
What about non-CMake based vendoring? Like, let's say somebody wanted to contribute the Bazel infra. Where would that go? Like, would that be part of the exemplar, or should individual libraries just say, well, we also support that, but it's not like a...
So basically, I think that anything that the project supports should be part of exemplar. I think that like it becomes challenging, and we've seen it become challenging where you have divergence, where you have some subset of libraries that have independent implementations of some kind of infrastructure or feature, but it's not backported into exemplar. I think what I want to move towards is that like all the features that you could possibly want are in exemplar, and then you just get it all for free by stamping it out. I guess one more, Jeff?
Sorry, yeah, maybe a final statement first. I think it's a tour de force, actually. What you've done here, basically, if you think about what Boost has done, you know, for 20-something years, right? We've now basically, I think, tipped over that level, right? The CI infrastructure now in Beeman is basically as strong as Boost, from what I can tell. Sans documentation stuff, and maybe a few things. So it's an amazing achievement to get it to this level. And I think maybe to Vito's question a little bit, I kind of think that if you're going to be serious about contributing to the standard, then there's no extra hoop jumping, right? This is the level of stuff that we should demand from libraries. And look, I get it, there's going to be a bunch of libraries that, you know, we're going to be looking at that aren't doing this, but then I think one of the things we've discovered over the last year is that, you know, we might find a volunteer, even if the primary author isn't willing in certain cases, to come and replicate that in Beeman itself, and then provide that consistent framework. So, yeah, I just think this is amazing work. Thank you so much.